Hey everyone, good morning, good afternoon, good evening. Welcome wherever you are in the world to this week 3 of our Machine Learning for Beginners series. Now, this is a conversation we want to have with you. We want you to get involved. We want you to jump in the chat, ask your questions, give us your comments. We'll be asking you questions. We'll be chatting with you. So the chat is there for you to use, but we do ask that you follow our code of conduct. We'll get a link to that dropped in the chat plus the text of it. But please, please, please follow our code of conduct. Basically, play nice, don't be a jerk, or we'll kick you off and ban you from all Microsoft events. That's how it works. But otherwise, welcome. Great to have you with us. As I say, we're here to answer your questions, so jump in the chat whenever you want to. And then once again, I'm joined by the amazing B. Stolnitz. So B, introduce yourself.
Hello, everybody. I am B. Stolnitz, and I'm an advocate on the AI ML team, and I focus on Azure ML and the Azure OpenAI service, usually. But today, I actually focus on teaching you about regression and answering any questions that you may have about it. So please ask me your questions and let's have a conversation. I already see here some familiar, I was going to say faces, but I actually don't know their faces. Some familiar names.
Yeah, Quinn Sab's back. Glad to have you with us, Quinn Sab, and Marek G. Great to have you
Good
with
morning.
us.
Good morning.
So yeah, feel free to jump in the chat, say hello, introduce yourself. And this series is based off some videos. So we dropped some videos at the start of the week covering regression, where B dived into regression, correlation, linear and polynomial regression, and categorical features. So let us know if you watched the videos. Let us know whether you've got any questions with that. Dariush is back with us as well. Welcome.
Yay.
Glad to have you with us. Great to have so many familiar faces.
Yeah.
Familiar names. Sorry, familiar names. Yes. So yeah, for anyone who's new, this is all about our Machine Learning for Beginners series. So we have this curriculum. Let me just add my screen to the stream. We have this curriculum. I'm just going to drop a link to this in chat if I can type properly, which I can't seem to do at the moment. Okay.ms/ml-beginners. So this is a curriculum that we've built. It's 26 lessons, free, open source, and walks you through classical machine learning. So it's completely free to use. It's got everything from quizzes and assignments, a whole lot of great stuff in here, teaches you everything around machine learning, and it's focused on machine learning around the world. So it's North American pumpkin prices, Asian and Indian cuisines, Nigerian music tastes, romantic hotels of Europe, you name it, you can do some machine learning against it. So that's the curriculum we built. It's been going for a while, translated into multiple languages. And then B and I have been working on a series of videos, something to those in the chat, where we actually go through the content. I say B goes through the content and goes through all the different sections in some of the lessons in the curriculum and actually shows you it and kind of teaches you those concepts. And then these live streams, this is our opportunity to hang out with you, work through it as well, and just dive in deeper and answer more of your questions. So this is the third week we've been doing these live streams. We've had a lot of great questions from folks covering everything from the basics of machine learning to careers, programming languages, and assembly language. At one point, we did veer off onto assembly language, which was a bit of fun. But yeah, so this is your opportunity to kind of join us. We're going to work through content and we're going to answer your questions. If you want to catch up on the last of the reactive videos, the ones where with the live streams, here's a link to a playlist that mixes the live streams in with the videos. So if you want to catch up on the discussion we've had in the past, you can find them all in there. But otherwise, welcome. Glad to have you all here with us. Marek says, I watched the videos. So yeah. Marek is clued up. So maybe Marek could answer our answer questions on logistic regression. If we get stuck, Marek, you're the one who's going to be answering the questions. And then Just For You's back as well, saying happy Friday.
Happy Friday. Happy Friday to you.
Yeah, glad to have you here. Just rolling into a nice weekend. Some of us, we've got Microsoft Build next week. Some of us have got vacation.
That would be me. Very happy about that.
Yeah, not that B's too smug about being off on vacation for the next 2 weeks.
Yeah, totally.
So Marek G says, no, thank you. I don't think Marek wants to be here answering the questions.
Okay.
It's all good. It's all good. So if you joined us yesterday, we were working through linear regression around pumpkin prices. So this whole thing we've been doing is around pumpkins. It's part of our around the world. And we were talking about kind of data cleanups and data science. We had some great questions around what the different libraries are used for. So what we did yesterday is we started off with a CSV file with pumpkin data, with different pumpkin sizes, different pumpkin data prices. And we're working with this to see whether or not we can predict pumpkin prices. This is kind of the goal of what we're trying to build by the end of today, is to actually better take a pumpkin price or take a day of the year and predict how much pumpkin is going to cost on that day. So pumpkins, big thing in America. Come Halloween, everyone buys the pumpkins and covers their doorways and porches in pumpkins and carves jack-o'-lanterns, and big thing in the US. So I'm British, obviously, you can tell from the accent. In the UK, we maybe buy a pumpkin and carve it. But the US, you're all about your pumpkins, aren't you Americans? All about the pumpkins. As you'd be, because obviously you're not American. So back home, before you moved to the US, were pumpkins a thing?
No, maybe to eat, maybe as an ingredient for cooking, but not like people don't put pumpkins on their porches, and also people don't celebrate Halloween even. So it's very different world.
It's definitely an American thing, isn't it? It's
Yeah,
in the US,
definitely. Yeah.
Because I mean, I've lived all around the world, and England does it a little bit. Trick or treating maybe, and you might have one carved pumpkin. New Zealand actually, in some places, would do it. There used to be one street that was just packed full of houses that were decorated, and trick or treating happened pretty much this one big street. But the rest of the world just doesn't
care. Yeah,
doesn't care.
Yeah.
Whatever.
Yeah.
So I guess actually, a question for our audience then: where in the world are you, and do you celebrate Halloween with pumpkins? Are pumpkins a thing?
Yeah.
Actually, I mentioned this the other week. I was doing a live stream for Halloween with some colleagues, one in the US and one in Australia. And we were carving pumpkins and then putting IoT devices in them to light them up, internet controlled light up pumpkins.
Nice.
But the colleague in Sydney, Renee, Sydney obviously doesn't do pumpkins at Halloween. It's the other hemisphere. So
Right.
Halloween is the spring. So she had a carved pineapple.
Nice.
That's what people do. They carve pineapples. So jump in the chat and let us know whether you've carved a pumpkin, carved a pineapple, or is this your thing?
Yeah.
So we getting back to our data. We had our pumpkin data. We're going to talk through this in the last couple of episodes, and we cleaned up our data. Kind of the first step of doing machine learning is data science. Your data needs to be clean. So we went through, we just got the fields that we needed. So we've got the day of the year, we've got the variety of pumpkin, the city it was grown in, and the price, and then a package measurement. So a volume. And we use that to work out a price per bushel, because pumpkins, if I get the data up here, come in loads of different packages, such as 22-pound cartons, 36-inch bins, 1 1/9 bushel cartons, whatever a bushel is. So we need to normalize the data. So we've been through, we normalized the data, and we created a new data frame with that in it. So this is our data. We worked out a price per bushel for everything. We then plotted it on a chart by month with price. Not that useful. We then did a plot by day of the year. We kind of got this whale shape. Here's the whale there jumping out the water, doing a spray. From pumpkins to whales, we have all the stuff in the Pacific Northwest. And we talked about this. We talked about correlation. There's no real correlation here. We actually measured the correlation, and this was minus 0.15. So we're basically saying that there is no real correlation between the day of the year and the price. Just those two values. And you look here, it's not like you can draw a line through this picture. But then we actually broke it down by pumpkin variety. And then we got a nice blue whale floating on a red sea. So we could see we had pie type pumpkins grouped together and miniature pumpkins grouped together. It's kind of got groupings based off pumpkin types. And so from that, we filtered it by pie type, and then looked at the correlation between pie type and price, and it gave us minus 0.26. So it's better. It's not perfect, but it's better. So then we moved on. Then we started doing some linear regression. So we actually trained a linear regression model using our pi-type data. So just the pi-type data. And what we found with this is we had an error of 17.2% or 2.77, which means that when we predict our pumpkin price, on average, we'll be out by anything by 17.2%. So that's not great, is it? Not great. And then we left it with a plotted a chart. So this is our pumpkin prices, and this is our line. And this is not very good. This is not very good. So this is where we got to. That's kind of a quick summary of where we got to yesterday. So today, do we think we can actually build a linear regression model that predicts pumpkin prices better? That is our challenge for today. So I guess, B, let's ask the audience, shouldn't we? So question for the audience, do you think we will get a better model?
Can Jim and I do it? So one thing, Jim, that I wanted to talk about, like we did touch on this last time. Somebody mentioned the p-value and asked, we kind of went on a rabbit hole saying, what is the p-value? But I wanted to kind of mention, I think it came up in the context of like measuring the quality or measuring the error of the neural networks. And I just wanted to make it very clear in case it wasn't clear in the previous video. So we don't use the p-value in machine learning to measure the error, or in regression to measure the error of the results. I know it's a very kind of commonly used statistical technique for statistics, but in this case, this is a different scenario, because in this case, we have actual values, not just the predicted values. So we can actually just use some sort of measure of distance between the actual results and the predicted results. So we don't just have, this is our prediction, is it good? We also have, this is what the prediction should really be. And so because we have that, it's almost like in a way, like a simpler scenario than most statistics. We're just really trying to measure the distance between what we got and what we should have got. And so for that reason, we use more like measures of distance, like the mean squared error. I've never heard of using the p-value in this context of machine learning, in terms of like measuring the quality or the error of a neural network, or not just a neural network, a regression model, or any kind of model, really. So I just wanted to make that very clear.
Okay, cool. No, thanks for clarifying that. Yeah, so it was Kevin who asked that yesterday. Yeah.
Okay.
So this kind of mean error. This is what, when we're thinking about the error here, then because we can actually work it out, the accurate number. We use that.
Exactly. Yeah.
Right.
So we have some answers to your question, Jim.
Oh, we do.
It's Halloween. Celebrate it.
So Marek says not celebrated in Poland.
Yep.
Yeah. Mike says SF. I'm guessing that's San Francisco. Yes, for Halloween. It has Celtic roots. The festival of Samhain, the Harvest Festival.
Nice.
Yeah, I mean, because there's lots of kind of roots behind it, because it's there's kind of All Hallows Eve idea, plus there is just the generic autumn celebration. You've brought all the harvest in, you've got plenty of food there to last you through the winter. Let's sort of celebrate the harvest. So yes, it is a kind of a good time of year for celebration. That's same as kind of around end of December. Yeah, that midwinter festivities. That's a very popular celebration all around the world, whether it's midwinter, whether it's December, whether it's midwinter for Northern Hemisphere, or July midwinter for the Southern Hemisphere. People like to celebrate with it's getting dark, so let's eat some of the food we've got. So yes, there's a lot of roots around these big festivals. So yeah, cool. And then Quinsab says, I saw a fun vid of different nationalities trying pumpkin pie, and the consensus was hard pass. Personally, I like it for Thanksgiving.
Do you like it, Tim?
I have never tried pumpkin pie, but I don't like pumpkin, squash, things like that. And I find a lot of American pies are way too sweet for me.
Huh. Okay.
So I've never actually felt the inclination to try it. Should I?
No, not according to me. Having lived here for 23 years now, I have had the opportunity to try it many times, and for me, it's a hard pass. So
Also, this is a hill I will die on. It's a tart, not a pie.
it's a
A
what?
pie has a lid. Pumpkin pie doesn't
It's a
have a lid.
tart, yeah.
It's a tart. It is a
Right, right.
and what a lot of Americans refer to as
Yeah.
pie is usually dessert tart, whereas I would die on the hill that a pie has a lid. I mean, even like a shepherd's pie,
Right.
it has a lid of mashed potatoes. It doesn't even have the sides; it has that lid. So a pie is all about. It's got to have that lid on it. The lid doesn't have to be pastry. You know, like a lemon meringue pie is a pie because the lid is meringue, but it's got to have a lid to be a pie. So pumpkin pie is a pumpkin tart.
Jim, he's like the dessert police. Dessert police.
There you go. I can put that on my social media. Dessert police.
New title for you.
Yeah, I love pie, and it's just weird when Americans talk about pie, but they're referring to a tart, and a pot pie is what I would call a pie. So,
Yeah.
and that's a different cultural thing, but yeah, that's a hill I'll die on. Pumpkin pie is a tart.
Yeah, totally.
Yeah, so Quinn Sub says no. If you don't like squash, you won't like pumpkin pie.
Yeah. Pretty much.
And then Fuzz would say, "Good point. We grouped pies and tarts together." Yeah.
Yeah.
Yeah. A pie has a lid. So. Right, so we have a question that's not related to pies.
We have a serious question. We actually have a serious question.
Serious question.
Good, thank you, Mohammed. So would you employ a linear regression model? So if you have data, in fact, Jim, do you still have your little images that you had yesterday? Like, so let's say if you plot your data and you have, let's say, 2 features, and your features are, it doesn't have to be 2 features, it could be more than 2 features, but we're just simplifying it here. You have one input feature and one output feature. And so if the points, if you plot those points and they appear to be like in a line, or they can be like approximated by a line, then you can use linear regression. So yeah, exactly. So in fact, we had some even before that had like linear, polynomial, and logistic regression. Do you remember those? Do you still have those around?
Oh, yes.
Just like in a previous video. Even before that.
Where are we? Same one.
No, after that. Yeah. So anyway.
No, we only got linear versus
polynomial.
So that's linear.
Yeah, exactly. So it's another example of linear. Like if you have a bunch of points that have a trend, if you see a trend in the points, and if that trend can be approximated with a line, if you're looking at the 2D case, then you can use linear regression. And how do you think of it in other dimensions? So let's say in 3D, if your points can be approximated by a plane, then you can use linear regression. And then in higher dimensions, then you can think of hyperplanes, which you can't really visualize them, but you can represent them mathematically. So that's when you'd use. Oh, and here we have the polynomial regression, right? So there's really polynomial regression is really just a special case of linear regression, and if your points don't approximate a line, but they sort of approximate some kind of like curve or like something you can draw, then you can use a polynomial regression, which is really just like linear regression, but you add more terms. You know, you can add an x squared, an x cubed, or if you have other features, you can, let's say if you have features x and z, maybe you can multiply x by z squared, x squared by z. So you can kind of keep adding terms to your function until you're able to come up with a function that kind of represents the trend of that data, regardless of how complicated it is. So that's when you'd use linear or polynomial regression. And so in these cases,
if you had like this, for example, when it's just all over the place,
then you can't make a good prediction, right? So there's little correlation, which means that you can't really find a trend. And if there's no trend, it's really difficult to make predictions, right? Then it's just like, you could get any result back, really. Yeah. And so we talked about.
Marek makes a good comment, actually.
Yes.
Care must be taken not to overtrain the model.
Exactly. So one common thing, in fact, you, Jim, mentioned this a few times already in these videos, is you can, if you make a line that goes through like every point instead of just capturing the trend, then you start overfitting. That's kind of the term that we use in machine learning, which means that yeah, you're going to do really well for your training data to predict the values in your training data, but you're not going to be able to generalize to new values very well. So even though it feels like, oh, I got every point right with my training data, in reality, that doesn't actually work very well to estimate, to make new estimations, to make new predictions, to use new points. It will, if it's overfitting, it will do well for the training data, but it won't do well for new data. So what you're looking for here is really to kind of represent the trend, not the exact points.
You kind of you want to have, take this picture, you want to kind of have the line that goes through with the points around it, kind of same here with the points around it. You don't want to join the dots, do you?
No, exactly. Yeah, if you join the dots, then you're overfitting, basically.
Okay, here's a question using words that I don't understand. How about generalized linear model in nonlinear correlation?
Yeah, so that gets more complicated. I'm not sure that I want to get into that. It is something that is like often, like if you take a course in university, these topics kind of start, you do learn about generalized linear models as you're learning these things, but we're going to keep it simple here. Let's keep it simple for this video. Otherwise we'll lose people. I can send you some links if you want to learn more about it. I think I still actually even have notes from university and all that, but for this video, let's keep it simple.
Yeah, outside the scope of this one.
Yeah, because I know we lose people easily when we start getting into this thing.
I mean, I don't even understand the words in the question, so I'm lost already. Cool.
Nigeria. Wow.
Yeah.
That's awesome.
Riodinu says hello to you from Nigeria Delta State. Yeah, you've joined us before, so welcome back.
Yeah.
And I think we've started something because Quinn Sab is going to have an argument at Thanksgiving this year about pumpkin pie being a tart.
Okay. Yeah.
I accept no responsibility. I would like to add Microsoft and the Microsoft Reactors accepts no responsibility for you having a Thanksgiving argument and pumpkin tarts being thrown at each other. So
yeah.
Cool. So I guess thinking about the kind of that question about how do you know about linear regression? If we've taken our data here and we've kind of got some points and kind of a line, and we've already talked about this is not good, haven't we? So if this is not good, obviously one thing would be, yes, linear regression doesn't work. That would be kind of one answer. But the other option is, can we make it work? Are there better ways to do it? Would that be the kind of the approach someone would take?
Yeah. Are there better ways? So like, can we use polynomial regression? Can we use more features? Can we use fewer features? Can we use logistic regression? In this case, we can't because we're predicting a value, not a class. But more features, fewer features, filter in some way, do some sort of like feature transformation. Yeah, I mean, if we can't, if we don't have good correlation, we can't draw a line to the points that kind of represents the trend, then we need to do something about it, right? Because we're not going to be able to get good results from this prediction.
And this is the thing where we have to kind of iterate, don't we? Because like we don't know what the right thing is sometimes, so we have to.
Absolutely. And that's why it takes like a lot of like thinking. It takes like a human that can actually make good decisions, and because there's a lot of decisions to be made, it's not an automatic thing. There's a lot of decisions to be made, and we're like, okay, so what do we do next? How do we solve this problem? And so in this case, what are we going to do first?
So actually, just you say it's not an automatic thing, but there are some tools that can help with that, aren't there?
There are, yes. So yeah, so actually in Azure ML, I'm not sure how much we should be talking about Azure here, but Azure ML is one example where we have this auto ML feature. There's other features like that in other products. So this is something that it's not new to Azure ML, but it's a feature where if you give it some data, the tool, the service Azure in this case, will try lots of different models, and you'll try lots of different hyperparameters for those models, because hyperparameters can change how the model works, the kinds of results you get from your model. So it tries a bunch of different options and trains it and calculates the how accurate, like the quality of your result, and then picks the best, right? And so you just let it run overnight. You do, or however long, depending on the size of your model, you let it do like 100 different attempts instead of having you do each one by hand, basically. And then you get the best one back, right? And so that's, these days, I would say, you know, this is a lot how people do, at least in Azure ML, I do see that this feature is used a lot. So definitely look into that. Like when you start, I think it's important to know how to do it yourself from scratch, but once you get a feel for it, then I think using these automated tools is a good way to go. And
Yeah.
and the reason why it's important to know how you do it yourself and to get a feel for it is that even when you use a tool, you still need to kind of, you can tell it, oh, use these 3 models only, for example. Like if you have a really good feel for it and I know I'm not going to get good results with this other model because I've used it for the scenario and it doesn't work. So these are the ones that I would try manually, if you already have that experience. And these are kind of the hyperparameters that I assume that they will work, then you can restrict the AutoML run to only try the models that you think are going to work and the hyperparameters that you think are going to work. And so then it's going to give you better results than if you let it try the whole world because you have no idea, right? So AutoML, I think at the beginning, especially when we put out the feature the first time, I saw that a lot of people were looking at it as like, oh, this is machine learning for people who don't know how to do machine learning. You just like press a button, it tries a bunch of things, and it finds what I need. But that's not, over time, that's not how I see it used when I talk to our customers. I see that it's a tool that is better used by people who know how to do these things from scratch and have a good feel for it, and then just need a little bit of help to automate the process. So absolutely,
So
that's
it's a tool there just to save you a lot of the grunt work. It's like you're looking here, we have a number of
exactly
features, rather than saying, I'm going to try this feature, I'm going to try
right.
this feature, I'm going to try these 2 features together, try this third one, these 3 together. Instead of you having to try those combinations, the tool tries the different combinations for you, but you kind of need to have that knowledge to say, yeah, here's the combination, here's the range of things you should try, and this is the model you should
Exactly.
try. So you need to have some smarts coming in.
Yeah, it really helps. I mean, you could obviously not have smarts and press run on the tool and get it to do something, but I think that if you have the smarts, you can get much, much better results. And that's what companies pay big money for these days, is people who have that intuition and who kind of understand how to use these tools. Mohammed has a really good question.
Hmm.
Um, Can linear regression handle categorical information? So linear regression cannot. Linear regression can only handle numerical predictions, but there's another type of regression that can, which is called logistic regression. I wonder, Jim, if you have a nice image there for us.
I
The
mean, like this
logistic,
one here, for example.
yeah, that one. Yeah. The logistic regression, like in here, like the yellow dots are your observations, like the points that you observed. So for example, you are trying to predict whether pumpkin is white or orange based on its size, for example. So you may, so let's say X is the size and Y is it white or orange, right? So you picked a bunch of pumpkins of different sizes and you plotted whether they're white or orange, and you plotted those yellow dots. So you're able to like fit this curve that you see in the green dashed line, which is like your logistic regression curve that will allow you to make predictions um, of like white or orange, basically, right? So like in the future, if you have a particular size, you plot, you look up the value of X, and then you kind of see where that falls in the dashed line, and then you get a prediction in Y. And if that prediction is lower than a certain value, for example, zero 0.5, then you'd predict 0, which could be, for example, orange. And if it's above 0.5, then you'd predict 1, which, let's say in this case, it's white, for example. So yes, not linear regression, but logistic regression can, and we do cover that in the course. So we do have a notebook for it. So if you're interested in that, take a look. Yeah.
Yeah, and we have some videos for that, hopefully dropping next week.
Yep.
Where you walk
Yeah,
through
on
it.
Monday.
Monday, hopefully.
Is overfitting a worse or less desirable outcome than underfitting? They're both bad. They're both bad. You don't want either, underfitting means you just don't have enough data, or you don't have a good enough model. You just need to like keep working on it until you start getting good results, because with underfitting you're getting bad results in your training data and you're getting bad results in your test data. So you just need to like see, what does it need? Does it need more data? Does it need a bigger model? What do I need to add to make this work, right? Overfitting is, in a way, it's not worse, but I would say it's almost less tricky, because it gives you this false sense of security, because you train and you get these amazing results and you're like, woohoo, I got it. I can do this, it's going to totally work. And then you try data that the model hasn't seen, and it just totally falls apart, right? So I wouldn't say it's worse, but it's more tricky. It catches people, like, people don't really see it coming. They think they're overconfident about their results, and then the models don't really work in the real world, right? So the idea is with, yeah, so you need to take care of both. Like you need to be able to recover from both, and there's many techniques for both.
So would this be, just think about where we are now with our line, would you class this as underfitting?
I would not. I would not say that that's underfitting. I just say that we just have data that has no correlation, that we just can't come up with good conclusions from that data.
Right.
At this point, we just need to look at the problem a little bit better, and we're going to, right? So people,
Let's do it.
Have confidence in us. Let's do it. Let's see if we can do better.
Yeah. So next I'm going to run, actually, I'm just going to run this line here. That doesn't work. Okay. Then reg is not defined. Then reg is not defined.
Oh, maybe you didn't run that cell.
Let me just run them all again.
The whole thing, yeah.
Just start again. So let's clear all the outputs. Clear all outputs, and let's just run the stuff we did before. Make sure it's all fresh. The data should have been there, but so
I was actually thinking there's one specific video that Mohammed, I think, could really benefit from. Let's see if there's one specific video. If you don't want to watch them all, there's one video where I talk about the differences between linear polynomial and logistic regression. It's like a 3.5 minute thing. Jim, would it be possible to find the link? Yeah, let's see. I think it's one of the maybe second week.
Introduction to regression models?
Yeah, I think so. I think it's that one.
So this one, we talk about differences between linear polynomial and logistic regression.
That's the one. Do you mind posting the link to that one? Because Mohammed, I really do recommend that you watch that one, because it explains what I just explained, but I think a little bit more concise and a little bit better.
Cool. Thanks for that, B. Yeah. Okay, so just rerun everything. And what we've got actually here, so if you remember back to some of the linear regression we talked about earlier, there's a formula, y equals a plus bx, or y equals mx plus c, or whatever is the different letters you use. And we can actually get those, can't we? So we've got this coefficient and intercept. So our equation is y equals minus 0.0175x plus 21.13.
Exactly. That's exactly it. Yeah. So essentially with regression, we found the a and the b in that equation. We have the y and the x, and we found the a and the b.
So if we make a prediction here, this is predicting it on 256th day of the year. We don't actually need to do any hard maths. We literally take y equals ax plus b. The a is minus 0.015. The x is 256. And the b is 21.
Exactly.
So I mean, literally, so I could do this. I could say
you could do that.
Minus 0.0175187 times 256. In fact, let's put some brackets around that. Plus 21.133734, and you see we got 16.648. So we're not running any models. It's just very basic maths, isn't it?
Yeah, exactly. At this point, in the prediction, the math happens during the training. You want the prediction to be quick, like even in these bigger models that you see, the large language models, whatever. We want the predictions to be really quick, otherwise they become unusable, right? The training can take months, years even. It doesn't matter, right? Because maybe not years, but like months can take, for sure. The current models do take months. But the prediction, it needs to be immediate, right? Because let's say if you ask ChatGPT a question on the web, you want it to be snappy. You want it to start producing words right away and not take a week, right? Yeah.
Yeah. So especially because linear regression, it is that fast, and because it's just simple. It's just you're not even running things through complicated networks that can take hours, take minutes. It is just multiply these numbers and add this.
Exactly.
Fraction second. Mark OS has a question. Isn't this when you use a correlation matrix?
Yeah, exactly. So we were looking at a correlation between variables. A correlation matrix, what it does, it gives you the correlation between every variable and every variable. So essentially, you'll have like typically a 1 in the diagonal because every variable has a 1 correlation of 1 with itself, meaning it's 100% correlated with itself. And then you have something else outside of that diagonal, right? You'll have some value. And so, yeah, we didn't do that here, but that actually would have been a good idea to put in the notebook. Because with the correlation matrix, you can see, I can, if you get high correlation between two variables, you can figure out, I can use this variable to predict that other variable because they're correlated, right? So there's some kind of relationship between those two variables. Yeah.
Okay. So if we're looking at so this is the data, we've got our clean data.
Yeah.
So if it turns out that there's a correlation between the city it's being sold in and the price,
yeah,
you buy it in downtown Seattle and you pay more than if you buy it in middle of nowhere, then if that correlation matrix shows it's got a high number, that's one of the features you should probably use, and that kind of feed into your. So like if you use tools like AutoML, where you say, here's the things to try, you can use a correlation matrix to very quickly say, well, there's zero correlation between this value and this value, so don't even look at those.
Yeah, exactly. Yeah, just focus on the so a correlation matrix would be a good idea to put here, and it's a good concept to understand as a beginning.
Yeah, it's actually good feedback for us. We should probably add that to this.
Yeah, I think so.
Yeah. So cool. So okay, so we've established linear regression is not our jam, isn't it? Linear regression is not cutting the mustard. So is polynomial regression better? So rather than a straight line, is it a wobbly line? Essentially. So we can use scikit-learn. Again, go back to Kevin's question about what libraries to use this. We're using scikit-learn to actually calculate the regression models. But essentially, we need to build what's called a pipeline, don't we?
In scikit, and I think it's because in this case, you really want to. So in this case, we're actually just using a x squared type of, actually like we have in the image that I think we created. I don't know if you still have that image, but so a wobbly line would try lots of things, but what we're trying here is just x and x squared, just those, y equals to b plus m1x plus m2x squared. And so in the code, I think we have a polynomial feature with a 2 passed as a parameter, and that means try up to x squared.
Okay. So again, just thinking about the idea of multiple iterations of this, we could then try if 2 doesn't work, we could try 3, 4, 5.
Yeah. Right.
But the more we have, the more overfitting we could get.
Right. Exactly.
Okay.
Yeah.
I was curious as to why there was 2 polynomial features.
Exactly. Yeah. So with 2, it's only going to give you either a curve like this or like this. It can't do more than that with just an x squared, like a function can't do more than that. With a 3, it can start doing like this. It can give you a wave.
Whatever it is,
right.
Thingy.
And then the higher level you go, then it starts being able to do all sorts of things. And then at that point, you can start going through every point, and then it can start overfitting. And if you see it overfitting, maybe that's one thing that you can scale back. Okay, let me not be so accurate with my training prediction line, and just see if I can represent more of the trend than the actual points, than every point. Yeah.
Okay. But again, I'm just thinking about the code that we're looking at here, because we talked about this before. So how much Python do you need to load to do this? It's not complicated code, is it? We're literally using an API, scikit-learn. We say make pipeline with 2 polynomial features, and it's linear regression, and we call fit.
Right.
We're not writing complicated mathematical code. It's just as long as you can call the libraries, as long as you can read this code, you can get started with machine learning. You don't need to be deep in Python code.
Right, right. And also the other thing is like even people who know a lot of Python, they don't know these APIs. So even if you learn a ton of Python, you're going to get here, you're still going to need to learn the API. And that's really the hard part here is the API, not the syntax, I think.
Okay, so let's run this.
Yeah.
So we've got a whole of, so what this is doing is just building a pipeline. We calculate the mean squared error. We score our pipeline, and then we do a scatter plot with our line on it. So if we look here, here's our line. It's got a bit more of a curve to it, but our mean error is 2.73 or 17%. So this is better, but we were on 17.2, weren't we? So we're not much better.
Exactly. Yeah, and you can actually see with the points, look at the graph, you can see, sure, a little bit of a curve maybe fits them better, but there's still a huge error between the points and the line, right? It's a huge distance between the points and the line. So when we measure the error, we're really measuring that distance between the line and each of the points. And that's still pretty huge.
We've got this model determination of 0.076. What is that? What is the model determination?
I forgot exactly what we put there. I forgot exactly what that means.
It's the pipelines.
I usually just use the mean squared error. So I forgot exactly what we mean by that. I think don't we explain that in the videos? Didn't we explain that?
I can't remember if we do
I
or
don't
not.
know.
It's been a
I
long
usually just use the mean squared error because I think it's very commonly used. And it's very understandable, right? Because it's like just a distance between the line and the points. It's a measure of distance.
Okay, so this is the coefficient determination. If the value is 0, it means the model does not take input data into account and acts as the worst linear predictor.
Okay.
It's simply a mean
There
value.
it is.
Value of 1 means we can perfectly predict all expected outputs. So we want a value that's getting towards 1.
Yeah, exactly.
Okay.
All right, so there's the explanation. Good.
A question on this from Marek that actually says, on the mean error, I was wondering if it's possible to optimize linear regression based on mean error so the model predicts better.
Yes, and then you have deep learning. That's what deep learning is. So you just explained deep learning with a very simple question, Marek. Thank you.
Okay, so deep learning is using machine learning models to optimize.
So deep learning is you get an error and then you use optimization to do back propagation. So go back through the neural network, change some the weights, and then see if it predicts better. And then you go back again and then forward. So you're basically doing optimization, essentially what you just said, optimize linear regression. You're doing optimization you're using the optimization, mathematical techniques that have been used for decades to get a better error out of your model. And that's why you totally got it, Mark. And this is why I think it's so important to learn regression before you learn deep learning. Because deep learning, if you start with deep learning because it's the important thing and the new thing, it's really difficult to understand it fully without starting with this. When you started with this and you start wondering things like you just did, can I just use optimization? I got an error, but like I can do better. Like if we just like use optimization, we could get a smaller error, right? Once you start thinking about these things, then you understand the next thing that's coming. Just naturally, you already understand deep learning.
Nice.
So that was really awesome. That was like a really nice moment in our.
So there you go, Marek. You are understanding this really well. You're well on your way.
You get a star.
Top of the class.
Yeah.
Marek has another question. How do you select the test and training data? What proportions? Should you do 70-30,
Yeah,
20?
or 80-20? Yeah. So there's many different, you'll see different people, or even the same person, even me, saying different things each time. I think when you have like smallish models, the numbers that you'll see commonly 70-30 or 80-20, where you just kind of said, right? So that's kind of common, take 20 to 30% of your data for testing. However, that's when we started working with these like large models, that's what the recommendations were. But I have seen the recommendations change over time. And so these days when you have millions, billions of data points, then you don't need 20% of billions to test. Like maybe you just need a fixed number. You need, 2,000, 5,000, and then you start not really thinking about percentages anymore when you start looking at these really, really big neural networks that have a lot of data. So for beginners, I think our recommendation is 70-30 or 80-20, because you're not going to be dealing with billions of data. You're going to be dealing with thousands of data points. And I think in that case, those percentages are fine. But just keep that in mind, that as you start working with these at a more advanced level, then you're going to kind of not really use those percentages anymore. And you're going to just start using your judgment a little bit better. And you're like, 5,000 data points is enough for us to test. We have billions. We're not going to do 20%, that kind of stuff. So yeah, so that's my answer to that. And Sean is asking, well, I think Jim and I neither of us are going to be presenting a build. I've always presented a build since I started my job, but I am going on vacation tomorrow. And so because of that, I did a lot of work for build, but it's all like behind the scenes work where you're not going to see me or my name in there. You're going to see my work in there, but not me or my name. And so yeah, this is the first time I don't present a build since I started this job.
Yeah, I won't be presenting a build either. I'll be there.
Yeah.
This is much my second time not presenting a build.
Okay.
I will be there. I will be on an Ask the Experts booth to talk about Azure Language Services.
Very nice.
So that should be fun. So yeah, if you're there, come find me in the Ask the Experts booth. But I'm not actually presenting this year, unfortunately. Do enjoy presenting at build, but yeah, not this year. I'm going to be hanging out in the expert build, asking people questions and answering questions. So
That's cool too.
Should be fun.
Yeah.
Cool. Right.
You know what, Jim? I can actually walk to build from my house.
Really?
That's the thing. There's a bit of a waste here. I can actually walk to the conference center.
We're flying people from around the world, and you can
Exactly.
walk there,
I could walk, and I'm flying away. But next year I'll present. Next year I'll make sure not to plan a vacation during build.
Cool. Okay, so 13 minutes. Can we do this? So we've talking about how we've looked at our model. It's not great. Even polynomial regression is not great. So we talked about, can we add more features? So one feature, it was the variety. Let's kind of put the variety in there to see whether that can improve things. But we can't put the variety in because it's just words, isn't it? There's no way, because these are mathematical models, and maths can't tell the difference between pi type and what have you. So we have to do some magic, don't we? One hot encoding is the magic. So what?
Yeah. So just as Jim explained, you can't input words into the model. In this case, your data is words, right? And you have 4 categories of pumpkin varieties. And so you need to turn those 4 categories into a number, right? You could just call them 1, 2, 3, 4. That could be one option, right? Easy, transformed 4 categories into 4 numbers. But the problem with that in this particular case is that by calling them 1, 2, 3, 4, which one is the 1, which one is a 2, which one is a 3? So by assuming an order, by assuming that, let's say, pi type is 1 and whatever else is 2, you're adding extra information to that data that wasn't there at the beginning. So you're adding an implicit order. You're adding that pi type comes before something else, whatever. And that information wasn't there. So you're really introducing kind of data that the model can pick up on that wasn't present in the original data that you collected. And so the technique to encode these into numbers without looking at order is this one hot encoding technique, where instead of using one feature for the pumpkin variety, you use 4 features. So you have 4 features that are true or false, or 0 or 1. And so let's say if number 70, the 70th pumpkin that we measure, if it's pi type, then we give it a 0 or false for all the other varieties, and we give it a 1 or a 2 or a true for pi type. So you basically expanded this variety feature into 4 features, or this one variety string feature, so into 4 features that are now 0, 1, or true or false.
Okay, so yeah, because
Okay?
it's just saying if you have that, if you give it numerical, you've got that implies an implicit relationship.
Yeah,
It's not. It's like like a size measure. If you're measuring the size of it from 1 to 10, it's kind of there is a relationship there.
exactly.
'Cause there could be something to do with a size 1 does one thing, and size 10 does something else, and 5 does something else. Whereas there is no way of doing fairy tale, miniature, mixed head, and varieties of pie type. There's no way of ranking those.
Right,
So
exactly.
we fake it
In
right.
fact, what you mentioned is that's totally it. So for example, if we were trying to encode, if we had a size, in fact, we probably do, if we had a size feature and the size had the, strings, the letters, small and medium and large, let's say, then I think it would be very appropriate to transform those categories into 1, 2, 3. Because then there is an order implicit to those words, right? Small, medium, large. You kind of think of them as a sequence. We don't think of it as small, large, medium, right? We think of them either as large, medium, small, or medium, small, medium, large, right? So those are like that's like the order that you would think. And because there's an order implicit to it, then if you encode them as 1, 2, 3, then you're not really messing with the information that was there. You're just encoding that information into a number. And so that's perfectly fine. But variety is not like that, right? Like there's no implicit order to these varieties unless there's like, I don't know, like these varieties, some of them are better quality than others, whatever. But then maybe you should have a quality feature that is separate, right? That kind of represents that order. And so that's what we do.
So again, this is kind of where you need a bit of help from a domain expert to actually understand whether there is an implicit relationship there.
Yeah, you need
Maybe not
to
so much in
hire pumpkin expert. Let's work with you on the problem.
Yeah, I mean, maybe not so much on pumpkins, but in general, if you look at like medical data, for example, it could be something does have a relationship and something doesn't. So
Totally.
Understand
Yes.
the domain is useful. So now
Yeah.
then, if we do the same thing and we use variety as our input, and we don't do linear regression, our error's worse. So if we just try and do a regression model of variety versus price.
Yeah, because maybe there's no correlation, right? We still just have like one feature. Yeah.
But if we
So
do
what
the same
happens?
thing,
But now we can add more features, right?
So rather than just do one, what we can do is we can say, let's add the variety feature and the month and the city it was sold and the package size, and to run a linear regression model on that.
Wow.
10%.
That's better.
That's better. So this is that iterative approach, isn't it? It's, well, let's just keep trying different combinations of features.
Right.
Because the variety probably impacts the price. You buy the little teeny tiny ones. It's going to be small. You buy a great big orange thing for carving. That's going to be more expensive, isn't it?
Right.
So the local pumpkin farm I go to, they charge by weight.
Yeah.
So maybe because of the bushel size, maybe there's something in that your bushel where it's got different pumpkins affects the different numbers of pumpkins in there affects the price because there's a certain cost to cutting the pumpkins. So if you've got a volume of this big and you can fit one pumpkin in, that's one cut. But if it can fit 100 miniature pumpkins in, that's a lot more expensive because people have got to cut.
Totally.
And then some cities are more expensive than others. So we're getting, as we add more features, we're getting better. And this is that iterative approach, isn't it? And that's linear regression.
That's linear.
But we saw polynomial was better. So if we do the same thing, use our same data set with all of our features with polynomial regression.
Even better.
9.5.
High five. How do we do a high five? I can do like that.
Kind of like,
yay!
But this is our model determination. This is 0.95. This is what we're saying. This is the number that needs to be close to 1, doesn't it? To say it's a good.
Yeah, exactly. Yeah, the model determination. That's what we saw, right? It needs to be close to 1. 0.95 is good, right? Pretty good. Like 95%. It's as good as it gets these days.
Yeah. So it's not. I mean, we're never going to be 100%, are we? Because that's when we get.
Then we're overfitting, probably.
Overfitting.
Yeah. If we're 100%, I would be very suspicious. I would just start. I just want to throw it some test data and see how it does. I mean, if it does 100% on test data, then we're fine, but it's very unlikely.
Yeah.
Yeah.
But there's still 9.5%. I mean, that's pretty good. So we're
Yeah.
saying when we look at pumpkin prices across the US, if we take into account the variety, the month, the city it was grown in or sold in, sorry, and the package, we can make a reasonably good prediction on the price
Yeah.
within like a
That's correct.
10%
Yeah.
error. And obviously, I know this is like we're just having a bit of fun here with pumpkin prices. But if you're a pumpkin wholesaler, if you are Kroger, for example, one of the big supermarket chains, and you're buying pumpkins by the bucket load because you want to sell pumpkins to folks who want to decorate their house, you care about this kind of stuff. You want to look at the historical data, and you probably want to bring in more data around things like weather conditions and um, yeah,
Yep.
things like inflation rates and all
Right.
manner of different bits and pieces, and you can use that to make an annual prediction of the cost of pumpkins. So, you can then say, right, well, you know what, when we're going to buy all the pumpkins for our stores in August because they're cheaper. Let's buy it on this day. So it can literally be used on a massive scale to save millions of dollars in pumpkin costs.
Totally. Even our little silly pumpkin example can have huge financial implications. And I could see actually somebody having this job and using this to save a ton of money for a company to bring in massive profits, right?
Yeah.
And that's why data scientists are so much in demand, right? Because just with a little bit of coding, you can actually save a company a lot of money, or
Hmm.
maybe save yourself a lot of money. Right?
Yeah. I mean, yeah, obviously, I think about it from a large corporate point of view. Yeah, if you're optimizing, you run this across all your fresh produce.
Right.
You're optimizing the time to buy milk to make cheese, or
Right.
all these other things. There's so many ways you can optimize all this,
Totally. Yeah.
and yeah, optimize supply chain routes and just everything. Even on a city level, you can use these kind of ideas to optimize public transport and travel and healthcare and spending. And there's just so much you can do by thinking about, I've got a massive amount of data. How can I manipulate that data to make decisions? This is a noddy thing with a CSV for the pumpkin prices, but the points being illustrated here scale so much.
Yeah, I totally agree. And I also think that people sometimes underestimate the data that they have, like companies do. A lot of times people think, oh, I need billions of data points to be able to do anything useful with machine learning. But the reality is you don't. And most companies have just can gather at least a few thousands of points of data points about something, and then try to understand that better and optimize it. And I think that can save them a lot of money to kind of think about the data that they have, and using making little predictions with it,
And that data
essentially.
can even become a new product in its own right. So I used to work for a
Hmm.
telematics company in New Zealand that the box in your truck to track whether or not you're on road, off road for tax
Hmm.
compliance and all that kind of stuff. And of course, they started gathering a whole lot of location data, speed data, and suddenly you can actually start rating people's driving. You can actually say to people, "Hey, this corner you got coming up, the speed limit says 70. You should be doing 30 in your truck because it's not safe." And then that
Right.
becomes like a safety product they could sell just by
Right.
being able to analyze vast amounts of data, build these models, and then run those on an individual driver basis to kind of say you're a safe driver, you're not so safe driver. That
Yeah.
then reduces insurance costs because they've got proof that, yes, I am safe. So you kind of pay the company to buy this report to say you're a safe driver to cut your insurance costs.
Yeah.
And that even fed up to like government level when there was a big earthquake, took out hold of roads. That data fed up to government level and used to actually set transport policy. So
Wow.
if
Yeah.
you've got this data, there's so much you can do with it, and that can become another product, or it can benefit people. Like literally when there was the big earthquake near Churchill, in the southern island of New Zealand, yeah, the trucks were going through tiny roads and they were ripping up the roads. So it's like, well, if we don't fix the big road now, it's going to cost us such a huge amount of money to fix the small roads. So we've got to throw everything at this, otherwise it costs us more in the long run. So many decisions can be made.
Yeah.
Um,
Totally.
it's cool.
Awesome.
So powerful.
Yeah.
Um,
Tim, I think we had some really good questions today. I think our
hmm,
audience today is like extra smart,
yeah.
extra high IQ.
I feel like everyone's learning things. That's what I feel like.
Yeah.
Yeah, the kind of the questions that are coming through are like, yes, we're learning stuff. So I feel like it's been a really good journey with everyone. We're actually,
Yeah.
there's a lot of people are picking this up. asking some very smart questions because they're understanding. So I feel like we've benefited everyone's learning.
Yeah, I totally agree.
So it's
Yeah.
great. So cool. We're pretty much at time. We do have to wrap up here. We should be dropping some more videos next week. Not sure whether we'll be back for more of these. We did talk about maybe doing some more when B gets back from vacation, but not sure. So please fill out our survey. Link in the chat. Let us know whether you want more of these, or there's other things we can cover. Let us know about the videos as well. We've got 13 videos, I think it is. So far, 4 more coming out this week to cover logistic regression for Mohammed's question. So yeah, let us know what you think. But otherwise, thank you for joining us. Thank you, B. It's been awesome hanging out with you.
Yeah, likewise.
I hope this is a really good session for everyone. And then carry on learning, keep wading through machine learning for beginners. Hopefully that will get answers to all your questions.
Yeah.
Marco asked a quick question about outliers. Check back some of our earlier videos. We had a really deep discussion about outliers. So if you go back and watch reactive videos, deep discussion about outliers, that should help you there. Otherwise, thank you everyone for your time. It was great to see you all, and enjoy the rest of your day and keep learning machine learning.
Bye. Bye, everybody.